Okay, let's continue with kernel synchronization. So this chapter is going to be more about like the basics of synchronization in the kernel. So there's two parts to this. Chapter 9 is the basics, and chapter 10 is basically the um, uh, kernel implementation of synchronization. So, yeah, let's get started. Introduction to kernel synchronization. In a shared memory application, developers must ensure that shared resources are protected from concurrent access. And concurrency usually means, as the book has said before, uh, the writing to shared data. So when it comes to multiple threads or multiple processes, reading data at the same time, that's not as big of a concern as if two threads, two processes, two of anything, or two or more of anything is wanting, to write or update data that is accessible by all of them. So shared data. And the kernel is no exception. Shared resources require protection from concurrent access because if multiple threads of execution access and manipulate the data at the same time, the threads may overwrite each other's changes or access data while it is in an inconsistent state. Okay, so let's parse that. So shared resources require protection from concurrent access. Okay, that makes sense, right? Like if we want to prevent data from being corrupted from multiple people actually touching it, we have to have some mechanism to protect it. Shared resources. That could just be like a variable or something like that. Okay. So if multiple threads of execution access and manipulate the data at the same time, the threads, so if the multiple threads, these threads may overwrite each other's changes or access data while it is in an inconsistent state. Now, the inconsistent state will usually mean basically a result that you had expected for it to be, but not. Concurrent access of shared data is a recipe for instability that often proves hard to track down and debug. Getting it right at the start is important. Properly protecting shared resources can be tough. Years ago, before Linux supported symmetrical processing, which is SMP, preventing concurrent access of data was simple. Okay, so at some point in history, Linux didn't support SMP. So when we were programming, we being any programmers, uh, they're writing code. They don't have to worry about this concurrency thing. Everything was always like single threaded in this case. Because only a single processor was supported, the only way data could be concurrently accessed was if an interrupt occurred or if kernel code explicitly rescheduled and enabled another task to run. Preemption. So your one thread is messing around with data, shared data, and then preemption occurs. Thread 2 comes in and messes around with that shared data. Well, then thread 1 coming back after it's now back with thread 2 being preempted, goes back and works on that data. It might be in a different state, for example. So that was like the only case the kernel had to worry about. With earlier kernels, development was simple. Okay, the those halcyon days are over. What the heck does this mean? I always hear it, but I don't even know what it means. Halcyon. First of all, let's find out what the definition is. Okay, so I don't know if anybody can see this. Let's zoom in. Okay. Denoting a period of time in the past that was idyllically happy and peaceful. Oh, okay, so like the whole rose tinted glasses days, like where you kind of just romanticize and fantasize about the past, the nostalgia, how it was so much better back in the day. Halcyon is how we pronounce it. Halcyon. Okay, halcyon. Okay, so those halcyon days are over. Symmetrical multiprocessing support was introduced in the 2.0 kernel and has been continually enhanced ever since. Multiprocessing support implies that kernel code can simultaneously run on two or more processors. Okay, so if you write code that can simultaneously run on two or more CPUs, then you can consider yourself to have multiprocessing support. Consequently, without protection, code in the kernel running on two different processors can simultaneously access shared data at exactly the same time. With the introduction of the 2.6 kernel, the Linux kernel is preemptive. This implies that, again, in the absence of protection, the scheduler can preempt kernel code at any point and reschedule another task. Okay, meaning the kernel can also be treated as a thing that could be shifted away from schedule with the scheduler. Today, a number of scenarios enable for concurrency inside the kernel, and they all require protection. All right. So this chapter discusses the issues of concurrency and synchronization in the abstract. So conceptual, not really truly related to the kernel, but just to get our basics down, as they exist in any OS kernel. So the concepts that we're going to be talking about are applicable to any type of kernel you're going to write. So the next chapter details the specific mechanisms and interfaces that the Linux kernel provides to solve synchronization issues and prevent race conditions. So the next chapter, being chapter 10, will talk about the specific concrete of what Linux does. Okay. All right. Okay, critical regions and race conditions. Okay, code paths that access and manipulate shared data are called critical regions. So they're just basically lines of code. So let's say if you had, some code. Okay, let's just say line 1, line 2, and then you had like some important line 3 with data, and then another important line. Okay, and then you'll have like line 4, then you have line 5. This part here, where you kind of want to make sure that if, let's say, thread 1 and thread 2 are actually executing each single line at the same time, or where they kind of interleave, you want to be able to protect this region where only one thread at a time can actually run. So let's say if thread 1 is running this section of code at this moment, with the proper protections in place, if thread 2 were to get to this region of your program, the lines of code basically, if it detects that, okay, somehow thread 1 is already executing this region here, it'll actually put itself to sleep temporarily, okay, until the next time it gets to run again. It'll check to see if anybody else is still in this section of the code, and if someone else is still in this section of the code, it's still going to go back and put itself to sleep for that schedule run. And if, let's say, no one is in this section of code, then it gets to execute. So we call this section of code the critical section, where only one thread can run the line of, or the block of code at once. And you do that through things like locks, mutual mutexes, so mutual exclusions, which is like a special semaphore. or you just have like regular semaphores, and then all that stuff. So we'll go over that soon. Just wanted to make sure everybody knew what critical section actually means in terms of concurrency. It's just basically a block of code that only one thread can execute at once. So then it is usually unsafe for multiple threads of execution to access the same resource simultaneously. Exactly what we just went over. To prevent concurrent access during critical regions, the programmer, so it's a responsibility of the programmer, must ensure that code executes atomically. That is, operations complete without interruption, as if the entire critical region were one indivisible instruction. It is a bug if it is possible for two threads of execution to be simultaneously executing within the same critical region. When this occurs, we call it a race condition, so named because the threads raced to get there first. Note how rare a race condition in your code might manifest itself. Debugging race conditions is often difficult because they are not easily reproducible. It's hard to kind of set your state of your environment up in a way where you can get two threads or multiple threads to kind of hit certain points of code at the exact like same time, or even like in a way where you can reproduce a certain race condition. And that's why oftentimes when we run into like bugs with race conditions, like this is not even kernel, this is like normal like programming with like where you're getting yourself into these weird bugs. You have to like try to reproduce it like many times until you actually are able to hit that exact condition, and it gets really hard. And that's the reason why like it's even you even run into cases where it's like, okay, you decide to go on this debugging session, and then you start adding logs all over the place to try and track this race condition. There are certain times where just by adding that log slows down a specific thread just enough that you never hit that race condition, and it just becomes exponentially harder to track down, because now you go from like 1 out of like 10,000 times where you can reproduce it. By adding a logging statement, now you've made it 1 out of 1,000,000 times, because you altered timing. In this case, you added like an extra operation. I've actually been in situations where a debug build never manifested a race condition because a debug build was just running so much slower than a production build. So these are, anyway, there's a reason why a lot of people don't like thinking about concurrency in terms of like knowing how it works deeply, and how to kind of just program in a way that keeps yourself safe, because of these types of things. Like there's like a notion that concurrency is very hard. It is hard, but it's doable in this case. Ensuring that unsafe concurrency is prevented and that race conditions do not occur is called synchronization. Okay, so we need to practice the art of synchronization to solve all the bad things that come from concurrency. All right. Okay, so actually I want to kind of like talk more about this critical region. So if we were to go back to a Scala draw, the book mentioned that, okay, a critical region should be like as if it was executed atomically. So atomically, right? As if, meaning execute as if it was one, right? Execute as one single instruction is what the book defined it to be. Okay, so now if you notice something here, a critical section is supposed to be atomically executed, so it's atomic like. Now, why do I claim it's atomic like, right? Atomic like? Is because first of all, this is not one instruction, right? Even this single line of code here, this one here, could be multiple instructions in assembly. This one here could be multiple instructions. So all of this is actually multiple instructions. So like, how do we actually make it so that it executes, like this critical section executes atomically as if it was a single instruction? And this is where I want to go back to the whole like locks and things like that, like these mechanisms, right? So by having like a lock here, like let's say lock, and then you have an unlock between here, so you have more instructions. Oops, unlock, a lock and an unlock. By locking this section here, that means whoever holds the lock, let's say thread 1, executing this critical section, they get to freely like execute code here without worrying that anybody is going to come in and also execute that same piece of code. And then when thread 1 is done executing that piece of code, it'll unlock so that it'll basically allow any other thread, process, whatever, to come in and also say, okay, I'm allowed to execute this piece of code now because I am able to grab a lock now. I'm grabbing that single lock that exists to say, hey, I'm allowed to come in and do stuff here. Nobody else is. And if you really think about it, given that no matter what happens, let's say thread 1 gets preempted in between here, for example, out from the scheduler into a ready state, from running to ready, and then thread 2 gets from ready to running, it can't even come into this critical region at all because thread 1 has obtained the lock in this case. So what happens is that you, like, just looking at it from that view, this is technically atomic now, right? Because it's allowing thread 1 to say, hey, I'm executing all of this at once without anybody coming in to come and meddle with what I'm doing. So if you think about it, that is executing as a single instruction. It's just not obvious in that case. But if thread 1 doesn't have to worry about anybody coming in, or thread 2 doesn't have to worry about coming in, then really, it's executing as one single instruction, just like really slowly in this case, or multiple. And it's kind of like a SQL database transaction in this case, like all these statements executing or nothing at all, rolling back, writing data to your database if any one of those statements fail. So yeah, I just wanted to make sure that's what the book means by atomic. It's just like, being able to execute critical sections of code as if it was like a single instruction without having to worry about like other things coming in and meddling with it. Okay, so why do we need protection? To best understand the need for synchronization, let's look at the ubiquity of race conditions. For a first example, let's consider a real-world case, an ATM, automated teller machine called a cash machine, cash point, or ABM outside of the US. So yeah, we're going to use like an ATM example, which is like a classic concurrency example to show you like what it means to, mess up concurrency and get into a bad state. So one of the most common functions performed by cash machines is withdrawing money from an individual's personal bank account. A person walks up to the machine, inserts an ATM card, types in the PIN, selects withdraw, and inputs a pecuniary amount. So I kind of know what this means. I just don't know how to say it. So let's do it. Pecuniary. So some arbitrary. So relating of consisting the money. Ooh, that's so detailed. More. Nobody even uses this word anymore, so I'm not going to invest in learning it. Pecuniary. Relating to money. It looks like the dictionary doesn't even know how to define it either. So yeah, no one uses it anymore, so forget it. Okay. Hits OK and takes the money and mails it to me. After the user has asked for a specific amount of money, the cash machine needs to ensure that the money actually exists in that user's account. If the money exists, it then needs to deduct the withdrawal from the total funds available. The code to implement this will look something like this. Okay, so basically what's going on here? The scenario is this. A person goes up to the ATM, puts in their card, types in the PIN, okay, so that's just like normal ATM flow, and then withdraws money, right? Attempts to withdraw money, inserts the amount that they want to be deducted from their balance, hits OK, takes the money, and then mails it to him for whatever reason. I hope it's just like, either he owes him money or yeah. Okay. So so that's like the flow, and here's what the code would look like, right? So you get the total amount from the account, so that's total. Then you get the withdrawal amount, that's withdrawal. Now, basically, if what you have is less than what you want to withdraw, then you have an error. You do not have that much money, and then you return -1. Okay? Now, you do have enough money. You're going to basically deduct the total from the withdrawal amount, and then you update the total funds to total. So, like, it's kind of weird, right? You would think like, oh, hey, I already updated the total here, but in the real world, this could be like a helper function that can not only update the total for the current ATM, but like update the total in the entire like real backend system for this specific account. So it makes sense to me here why you have like, you update total, but then you have to really update total funds here. And then spit out money, give the user their money. This is probably some helper again, like not only just to give the money, but to kind of update everything else in the entire like system. So yeah. Okay, so you can see like you're doing a lot of updating here on data that can actually go and result in something that you wouldn't expect if more than one thread were to be executing this at the same time. And we can think of another thread as if, let's say, who's the character here? A person. Okay, let's say that person's wife is in another city, right? Let's say she wants to get gas in somewhere else because she's like commuting to work. She also shares the same checking account, for example, and then also goes up to that ATM at the same time. So happens. Okay, so at that point, you can see that, okay, what she sees as a total is going to be the same as what I see, okay? But then going down through the whole flow, let's say that person is slower to like input things, and then that person's wife is probably inputting much faster to withdraw. At that moment, that person still sees that same amount of money that they started out with, and it's no longer the case because money has been withdrawn elsewhere. So you can see like how there could be a lot of potential race conditions that can result in really weird results down the line. So let's say, okay, so here it is, right? So now let's presume that another deduction in the user's fund is happening at the same time. It does not matter how the simultaneous deduction is happening. So assume, okay, this is the same example. Assume that the user's spouse is initiating another withdrawal at another ATM. A payee is electronically transferring funds out of the account, or the bank is deducting a fee from the account, as banks these days are so wont to do. Wait, what? A payee is electronically transferring funds out of the account, or the bank is deducting a fee from the account, as banks these days are so wont to do. I guess that's what they love doing. Any of these scenarios fits our example. Okay? Both systems performing the withdrawal would have code similar to what we just looked at. Basically, first you always check if the deduction is possible, then compute the new total funds, and then finally execute the physical deduction. So it doesn't matter what type of system they're working with. It's just that we're just concerned about this flow here, right? We're just basically concerned about just simply withdrawing money. So now let's make up some numbers. Presume that the first deduction is a withdrawal from the ATM for $100, and that the second deduction is the bank applying a fee of $10 because the customer walked into the bank. Assume the customer has a total of $105 in the bank initially. Okay? Obviously, one of the transactions cannot correctly complete without sending the account into the red. So I'm just gonna use myself. Okay, so I have $105 in the bank right now, and I want to withdraw 100, right? But then also when I withdraw 100, I actually don't even know my bank's terms of use, and I don't know that the bank's gonna deduct a $10 transaction fee on me just because I used the ATM. So then the total here is going to be $110, but obviously that's not going to work out because I only have $105. And this is going to happen at the same time. Okay, so once I withdraw $100, the bank's going to withdraw $10 from me. Okay, so what you would expect is something like this. The fee transaction happens first. So I take out $100, now I only have $5. $10 is less than 105, so 10 is subtracted from 105 to get a total of 95. Right? Oops, the fee transaction, not me. So the $10 is first. So $10 is first to get 95. And then when I come along and withdraw, it fails because 95 is less than 100. Because I wanted to withdraw 100, but only 95 was in the balance. So this is like an example of like how there's no concurrency. Everything's like happening serially in this case. Okay? With race conditions, life can be much more interesting. Now, this is the new scenario. Assume that the two transactions are initiated at roughly the same time. Okay? Both transactions verify that sufficient funds exist. So $105 is more than both $110. That is true. If both transactions are happening at the same time, both transactions will see that the total is $105 at that point. So then they're like, okay, well, good. 100 is less than 105 and $10 is less than 105. So let's just withdraw. So then the withdrawal process subtracts 100 from 105, yielding 5. And the fee transaction then does the same, subtracting $10 from 105 and getting 95. The withdrawal process then updates the user's new total funds to $5. And then after that, it just so happens that the fee transaction also updates a new total, resulting in 95. So now, okay, the final state is that I went to the bank, I had 105 before, I withdrew 100. I was supposed to get $5, but at the same time, my bank fee saw that my balance was 105, deducted $10, and now the final balance is 95. So I really, got $100, but yet I only lost $5 at the same time. So clearly, financial institutions must ensure that this can never happen. They must lock the account during certain operations, making each transaction atomic with respect to any other transactions. Such transactions must occur in their entirety without interruption or not occur at all. So yeah, let's first of all visualize the last example, okay? So remember that the code was here. This is the code, just for example. We get the total from the account, which is $105, right? And then we specify the amount we want to withdraw, which is 105 or $10. Okay. Now, this is where it gets really interesting. Let's not consider this right now. We both know that we both have enough funds. $100 is less than 105, and then $10 is less than 105. So let's just simplify this and not consider this. But the interesting one is here. So basically what's happening is that bank and me come in, we're doing all this at the same time. We're at the same time in sync with this, okay? Then at some point I withdraw, when we both withdraw at the same time, okay? we both withdraw at the same time because now we have this. We start with the same total and we withdraw at the same time. But let's say I got preempted at some, or let's say no, the bank got preempted now. So then now I get a chance to run still, and I now update my total to be 5. Okay, and then now I am going to then take my money, and then somewhere down the line, the bank gets scheduled back and executes code where it left off, which is here. Well, in its own stack in memory, whatever it is, it's like local variable, whatever you call it, is now still at 95, right? So then it updates the total funds to be 95 in this case. And this is a stack memory because right here it's saved a variable here in its local function here, so it has to be in its stack. So that's how you could end in that situation. So basically, whoops. So if we're looking at this here, so this is me, this is bank, okay. So at some point we both start with 105. We see that we're in sync, okay. And then what I do is I'm going to withdraw 100 and the bank withdraws 10. Okay. Now the bank goes to a state where it is sleep. Well, first it updates the total, right? So it's now 95, and then it goes to the queue, right? So it gets preempted, and at the same time here we're still synchronized, right? So I have 5 at the same time, but I didn't get preempted. I'm still executing, so I update. Right, I update. Okay, so now the balance is 5. Okay, and then I take my money and I walk off. So now the bank wakes up again, and now they update their total to 95, and then they take the $10. So what's the final balance, right? The final balance is pretty much the latest one. Not this one, but this one. Because in the timeline here, 95 is the latest one. So that's why I ended up with $95 still, even though I have taken away $100 in my pocket. So, and it could also go the other way around, right? Like another scenario here, okay, is, okay, if it's me, and then there's a bank. Okay, let's say the other scenario is 105, and then let's say now I take no, let's say the bank goes first, right, and takes like $10, and then I get preempted. Okay, I get preempted, and then still having that total, right, I take out 100. Okay, and then the bank at the same time, or at somewhere down the line, updates to 95. Okay, and then takes the $10. Okay, well here, let's say I get the new total is going to be what, update to 5, and I take 100. Right? Still, it's still a bad state because I end up with $5 in the balance as my balance. But even though like that math didn't work out, I'm supposed to be in the red in this case. So I still have money that I shouldn't be having in my bank account. So there needs to be like some sort of synchronization. The right result here actually would have been like error, you don't have enough money on either side. That's like the real answer here. But regardless, it's like because we have no protection from concurrency, we end up in the state where we could either always have some money, a lot of money, or and accidentally this all works out, one of us can't withdraw. So okay, all right, so the single variable. Now let's look at a specific computing example. Consider a simple shared resource, a single global integer, and a simple critical region. The operation of merely incrementing it. I plus plus. So let's just consider this single operation, this single increment of I. This might translate into machine instructions to the computer's processor that resembles the following. So this single increment, okay, it actually does a lot in machine code. So let's see what it is actually doing. So it's get the current value of I, okay, in memory, in the memory address, okay, and copy it to a register. Okay, so already you can think, if you think of basic assembly, that's already two instructions, right? Or maybe one single instruction. Basically, some sort of move instruction from a memory location into a register. Okay, that's one instruction, one line of assembly. The next line of assembly is now we add 1 to the value stored in the register. So it could be like register EAX equals register EAX plus 1 or something like that. Now it's still in the register, but you need to put it back into that memory location that represents I, right? Because you had gotten that value from I in that memory location, incremented it in that register because CPUs operate on registers. Now you take that new value in the register, you need to update the memory location where I exists. So that's right back the memory to new value of I. So you got 1, 2, 3 instructions here. So that's one thing that we might think about in high level languages, is that I++ is just like one single thing, right? Big deal. But in reality, it could be up to 3 instructions for the CPU. Okay? Now, let's assume that there are 2 threads of execution. Both enter this critical region, and the initial value of I is 7. The desired outcome is then similar to the following, with each row representing a unit of time. So thread 1, thread 2, okay? And this can be many things, right? Like this can be 2 threads inside a single core, or could be, and where each one of these threads hold a task, a process, right? So that's how it is, right? In software form, a thread is basically some sort of unit of execution. Each one of those threads is assigned a hardware thread, right? So you have 2 in this case. So let's say the first thread, right, and your CPU is running this program and gets I, which is resulting 7 from memory. Okay, so I is 7 in memory at this moment. Thread 2 is idle, not really into this program right now, executing some other program in the CPU. Okay, now going back to thread 1, we increment I to 7 to 8. This is the register part, and then we write back I right away. So we update the location memory with 8 that represents I. Okay? Yeah. All right. Now let's say somewhere down the line thread 2 wakes up. Okay? So now it gets I, because you're running this code concurrently. Okay? You'll get I, it's 8 from memory. Then you increment it, in your register 8 to 9. Then you write back 9 to the location in memory that represents I. That's good. That's correct, right? Like that's what you want. If there's 2 threads that are operating on the same piece of like code, a program, well, if you have 2 threads running, you're incrementing twice. You should increment by 2 instead of 1 at the end of it all. So we go from 7 to 9 at the end of time. And that makes sense. That works, right? So as expected, 7 incremented twice is 9, a possible outcome. That is possible, right? That is one of the combinations that can happen. That's a good one. That's a good case. But let's look at a bad case. Let's see what happens if thread 1 and thread 2 actually go in at the same time and do things and start interleaving with each other on that same program. Okay. So thread 1 and thread 2 now both get I at the same time from memory. 7. Okay? 7. And it's assigned to the register. Okay, at this point you remember that registers are kind of, every single task gets their own state of the registers of the CPU, right? So then, in their view of the world, they're at 7 in this case, because that's what it was in memory at the same time they picked it up. Okay, so now thread 1 is going to increment whatever's in the register, right, from 7 to 8. Okay, thread 2, something happens, it's kind of slow, whatever. Eventually gets to it. Well, it's going to increment in its register, right? In its own register, it is 7 still, because that's what it was in its register. It goes from 7 to 8 too. Okay, now thread 1 somehow kind of wakes up again, or realizes that it needs to keep running. It updates the location in memory that represents I, and remember, this memory is shared to the value 8 in this case. Thread 2 also does the same thing with its result, 8. So you have 2 threads that were trying to increment I. You intended for it to increment twice because you have 2 threads incrementing I, but they somehow got the value at the same time to be 7. So then they increment. They did their job. They did do incrementation twice, but they didn't increment I to the value of 9 in this case. It both ended up with 8 because they both saw the state of the world at the same time, and then they did things to it. So yeah, that's wrong. So if both threads of execution read the initial value of I before it's incremented, both threads increment and save the same value. As a result, the variable I contains the value 8 when in fact it should now contain 9. This is one of the simplest examples of a critical region. So yeah, this should have been locked, right? Like only one thread should have been able to do these 3 lines of code here. So thankfully, the solution is equally as simple. We merely need a way to perform these operations in one indivisible step. Okay. Most processors provide an instruction to atomically read, increment, and write back a single variable. Okay. Before I go further, I want to make sure everyone knows that at any point in time, the reason why these things happen, these gaps happen, is just because you have to remember that a thread or any other task or process or whatever, right, can be preempted at any time, even in a critical region where they have obtained a lock. It just so happens when they get preempted, if they have the lock, as long as they hold that lock, the second thread coming in cannot execute that piece of code and will just sleep even more, resulting in more of these things here. If you were to imagine this as like a flow chart or whatever you call it, like a time chart. So you have to remember, at any time in user land or whatever you call it, user space, if your program is running, it could be preempted at any time. Okay, anytime. Even if you hold a lock, it just so happens that you're still safe because you hold the lock. You don't have to worry about anybody coming in and meddling with your critical code. Okay. So just trying to clear that up. Most processors provide an instruction to atomically read, increment, and write back a single variable. Using this atomic instruction, the only possible outcome is increment and store, increment and store. So 7 to 8, 8 to 9. So this, what he's trying to say here is that, let's say we had one instruction, like a CPU instruction that can take some value in memory, put it into a register, and then increment it, and then store it back into the memory location in one shot, just like one single line of assembly. There is actually in x86. So in x86, so that, she shows you the example, like if thread 1 came in and thread 2 came in after, or thread 2 came in, thread 1 came in after, yeah, you still result in the same value. But basically, there is one. Okay, so it would never be possible for 2 atomic operations to interleave. The processor would physically, so the processors with this type of instruction, this instruction that could do all of these 3 operations in one, it would physically ensure that it's impossible for 2 threads to concurrently increment and store a specific value. So using such an instruction would alleviate the problem. The kernel provides a set of interfaces that implement these atomic instructions as they are discussed in the next chapter. So there's a physical way to do it, but it's very simple. It only does these types of values. But obviously in the real world, like we saw before with this critical region right here, it's doing a lot of things, not just like taking a value and incrementing it or doing that one single operation, right? So the kernel provides in the software a way to simulate that with the locks and everything to make it act like it would be executing in one shot. So locking is the simplest way to do it. So locking. So now let's consider a more complicated race condition that requires a more complicated solution. Assume that you have a queue of requests that needs to be serviced. For this exercise, let's assume the implementation is a linked list in which in which each node represents a request. Okay, let's assume we have a linked list, okay, and we have a queue that contains requests. Okay, so this queue is implemented as a linked list, got it, and then each node is a request. So each item in the queue is a request. So we have two functions that manipulate the queue. One function adds a new request to the tail of the queue, so at the end of the queue, and another function removes a request from the front of the queue, the head of the queue, and does something useful with the request. So one is adding to the queue, one is taking away from the queue and does something with the request removed from the queue. Various parts of the kernel invoke these two functions. Thus, requests are continually being added, removed, and serviced. Okay, manipulating the request queue certainly requires multiple instructions. If one thread attempts to read from the queue while another is in the middle of manipulating it, the reading thread, so the thread that is actually reading from the queue, will find that the queue is in an inconsistent state because another thread is modifying the queue at the same time. So it could not even have a source of truth here. It should be apparent the sort of damage that could occur if the access to the queue could occur concurrently. Often, when the shared resource is a complex data structure, the result of a race condition is corruption of the data structure. Okay, so we can leave the data structure in a bad state, or even like minor cases, like a state where it doesn't reflect the most up-to-date information. So the previous scenario at first might not have a clear solution. How can you prevent one processor from reading from one queue while another processor is updating it, right? So again, if you have multiple threads, your CPU, if you have like a multi-core CPU, it has several hardware threads, and that makes it possible for each thread to go into a specific hardware thread and execute at the same time. So how do you protect this? Although it is feasible for a particular architecture to implement simple instructions such as arithmetic or comparison atomically, let me read that better. Although it is feasible for a particular architecture, say x86, to implement simple instructions such as arithmetic and comparison atomically, so meaning that it is possible for x86 instructions to implement simple arithmetic like add, subtract, divide, multiply, or comparison greater than, less than, equal to, whatever. They can do this atomically, right? But it is very, very hard for architectures to know all the cases of what you want to do and provide instructions to support all types of concurrency handling, like this queue handling, for instance, the indefinitely sized critical regions that would exist in the previous example. Okay, so what the processor will provide are like those simple building blocks, right? And it's up to the software developer to take those concepts and actually create additional types of code that can help you with protecting these bigger operations and simulate that atomic thing. What is needed is a way of making sure that only one thread manipulates the data structure at a time. A mechanism for preventing access to a resource while another thread of execution is in the marked region. So mechanism, we need this thing, right? this thing. This thing is called a lock. A lock provides such a mechanism. It works much like a lock on a door. Imagine the room beyond the door as a critical region. Inside the room, only one thread of execution can prevent or can be present at a given time. Okay, so inside a room, so this is real life, only one thread of execution can be present at a given time. When a thread enters a room, basically because it has that lock to the door, to the room, okay, when it enters, it locks the door behind it. So now it has a key, it's inside the room, right? And it locks the door so no one else can come now. So when the thread is finished manipulating the shared data, it leaves the room and unlocks the door. Okay? If another thread reaches the door while it is locked, it must wait for the thread inside to exit the room and unlock the door before it can enter. So let's go back to the whole sleeping thing. Let's say that thread unlocks the door, goes in, locks the door. Now it has a key inside the room. The door is locked. It can actually just sleep, right? And any other thread coming in from the outside can't open the door at all. It has to wait. Okay? And if it's too long, the other thread goes, whatever, I'll just go to sleep myself too. And that's what I mean by the thread 2 will always go to sleep. And then eventually it wakes up, it checks again, it just, wiggles the doorknob, see what happens. And if it's still locked, then it does the thing over and over again. And if thread 1 continues to sleep indefinitely, then we have something called a deadlock, or no progress is being made. But if thread 1 eventually wakes up, gets out of the room, unlocks the door, gives the key to someone else, then progress is made. So anyway, thread hold locks protect data. Okay. In the previous request queue example, a single lock could have been used to protect the queue. Okay. Whenever there was a new request to add to the queue, the thread would first obtain the lock. Okay. So basically when we're ready to add a new request to the queue at the end of the queue, that operating thread must obtain a lock. So now no one can touch the queue. Then it could safely add the request to the queue and ultimately release the lock. So it's usually just like a function call, like lock, and then do your thing, and then unlock. So when you're writing your program, you have to implement this. When a thread wanted to remove a request from the queue, it too would obtain the lock. So the other thread which wants to remove it has to obtain a lock the queue part, like that section of removing stuff, and then do whatever it needs to do and then unlock. Then it could read the request and remove it from the queue. Finally, it would release the lock. Any other access to the queue would similarly need to obtain the lock. Because the lock can be held by only one thread at a time, only a single thread can manipulate the queue at a time. If a thread comes along while another thread is already updating it, the second thread has to wait for the first to release the lock before it can continue. The lock prevents concurrency and protects the queue from race conditions. Any code that accesses the queue first needs to obtain the relevant lock. If another thread of execution comes along, the lock prevents concurrency. So here it is. Thread 1 tries to lock the queue. It succeeds, it acquires a lock. At the same time, thread 2 tries to lock the queue. Well, since, at this point, atomically we can acquire the lock in one shot, thread 2 found that thread 1 beat him to it. So then it just goes to sleep, waiting, while thread 1 is doing stuff with the queue, unlocks the queue. Thread 2 wakes up again, it acquires a lock, and then no one else can now. If there's a thread 3 right here, it'll be like waiting. It does its thing and unlocks the queue. So, yeah, it's simple. It's real simple. It's just like a function call. In your code, you would just say lock with some object that everybody can read as an argument. Do your thing, and then unlock. It's a function call too. So notice that locks are advisory and voluntary. So this is very important. Okay, locks are entirely a programming construct that the programmer must take advantage of. That means the programmer determines what the critical region is. Okay, so let's say you write a program and it's like a multi-threading program. So because you want performance, right? You want multiple threads to do things at once. Now, you only get the benefits of multi-threading if you are actually allowing multiple threads to actually work at the same time. But let's say you lock really big chunks of code, now you've effectively kind of just stalled other threads from making progress whenever a thread is working inside that big critical region. So it makes sense for you to like think about it like in terms of what is like the minimal amount of code I can like lock, like to define as a critical region and lock, so that everywhere else everybody can continue to do work. Okay, so that's like the hard part about concurrent programming. It's just the fact that you need to like really think about your cases and like what is appropriate. So yeah, nothing prevents you from writing code that manipulates the fictional queue without the appropriate lock. Such a practice, of course, would eventually result in a race condition and corruption. So you can do whatever you want with the lock. How you do it is just up to you. So locks come in various shapes and sizes. Linux alone implements a handful of different locking mechanisms. The most significant difference between the various mechanisms is the behavior when the lock is unavailable because another thread already holds it. Some locks variants busy wait, whereas other locks put the current task to sleep until the locks become available. So Linux has like two, like there's like a spin lock where if a lock is acquired and you want to get that lock, you'll just like stand there like always trying the door repeatedly, like maybe every, I don't know, 2 seconds. That's like busy waiting. Versus like there's another type of lock where you go, whatever, I don't care, I'm just gonna sleep. When I wake up, I'll just check again. So the next chapter discusses the behavior of different locks in Linux and their interfaces. Okay, let's finish this paragraph and let's just call it. So astute readers are now screaming, the lock does not solve the problem. It simply shrinks the critical region down to just the lock and the unlock code. Probably much smaller, but sure, it's still a potential race. Well, fortunately, locks are implemented using atomic operations that ensure no race exists. So what they're saying is that these operations, these acquisition and unlocks, are atomic operations underneath the hood. So you don't have to worry about like two things trying to lock at the same time. That's not the case here. The CPU will physically determine which one will get that lock because they are atomic in this case. Okay, so a single instruction can verify whether the key is taken, and if not, seize it. How this is done is architecture specific, but almost all processors implement an atomic test and set instruction that tests the value of an integer and sets it to a new value only if it is 0. So yeah, you're starting to kind of get a sense that locks are just simply like flags. But it's a special flag that allows you to get it and set it all at once. And that's like the whole incrementing I example. A value of 0 means unlocked. On the popular x86 architecture, locks are implemented using a similar instruction called compare and exchange. So compare and exchange is that instruction in x86. Okay, well, that's made a lot of good progress. Hopefully, that's a good start to trying to understand concurrency, and we'll continue next time. Thank you. Bye.